Hello my dears, how are you all? So what we studied in the last class? My dears? Some method, right? Resistance measuring method and electrodynamometer type instruments, right? Those are very, very important. Today I am going to discuss a very important session. It's actually a small topic, but questions may be asked from this. Dissipation factor. Dissipation factor. Listen my dears, consider an RC parallel circuit, okay, consider an RC parallel circuit in which what I1 is the current flowing through resistor and I2 is the current flowing through the capacitor and I is the total current. So when I drawing the phasor diagram, what I get? When I drawing the phasor diagram, suppose I am taking V as the reference value, let it be V as the reference value, then I1 will be in phase with my V. Is it correct now? I1 will be, because it is pure resistor. Assume both are ideal because it's pure resistor and pure capacitor. Okay, assume both are ideal. So what happened? This I1 will be in phase with my the voltage because it is resistor, and I2 will be what, my dears? I2 will be what? 90 degree away, leading from the what? Voltage applied. This is a basic principle now for inductor and capacitor. You know this very well. So what happened here? The resultant current I will be like this. And this is nothing but the phase angle. Phase angle is nothing but the angle with the voltage and the resultant current is called the phase angle. Another angle is also formed here, my dears, which is called the let it be theta. Another angle is also formed here, which is called theta. Then dissipation factor is nothing but tan theta of loss angle or loss tangent. Which means this theta is called, this phi is called phase angle, you know that, and this theta is called loss angle or loss tangent. So the tan of the loss angle or the loss tangent is known as the dissipation factor, and dissipation factor is denominator, represented by D, and D is nothing but tan theta, or I can say that D is not equal to tan of theta is nothing but minus 90 minus 5. Tan of 90 minus 5. So that is called the dissipation factor. So in RC parallel circuit, from this diagram, what is tan theta? From this diagram, what is tan theta, my dears? So tan theta is nothing but, from the diagram, from the phasor diagram, tan theta is equal to, I can write like I1 by I2, am I correct? Because tan theta is nothing but opposite side divided by adjacent side, am I right? Opposite side is nothing but I1, adjacent side is nothing but what, my dear? I2. Or what is I1? I1 is nothing but the current through the resistor, which is nothing but V by R. And what is I2? I2 is nothing but the current through the capacitor, and which is nothing but what? V by omega C R, correct? V by omega C, not R, because IC or I2 is equal to voltage divided by its reactance. So V by XC, right? V by XC na. So XC is V by XC, correct? V by XC. So V by XC means I can write like this. So it will be V by R divided by V by XC means V by 1 by C omega, correct? Correct. XC is nothing but, my dears, 1 by C omega, or it will become what? V by R into or divided by V by 1 by C omega become V omega C, correct? So it will become V and V get cancelled, 1 by RC omega, 1 by RC omega, 1 by RC omega. Okay, so from the phasor diagram, tan theta is equal to 1 by RC omega. Did you see it somewhere? 1 by omega RC. Did you see it somewhere? This equation 1 by omega RC. Did you see somewhere? Did you see somewhere, my dear? Did you see somewhere? Did you see somewhere? What is the Q factor for series RL circuit? So series RC circuit. What is Q factor for series RC circuit? See, Q factor is nothing but, my dear, Q is equal to XL by R or XC by R. XC is nothing but 1 by C omega into R. See, Q factor is equal to 1 by C omega, which means for series RLC circuit, XC by R is nothing but 1 by C omega R, and you forgot the same thing here. You got the same thing. That means the dissipation factor or the tan theta or dissipation factor of the parallel RC circuit is same as that of the Q factor of the series RC circuit. Am I right? The dissipation of the dissipation factor of the parallel RC circuit is nothing but the okay, and see the Q factor of this is a series RC circuit, and the same will be, what is the Q factor of parallel RC circuit? Parallel RC circuit. Parallel RC circuit Q factor will be nothing but Q is equal to what, my dear? The reverse, right? The reciprocal. It is nothing but omega CR. Omega CR. So you compare these two things. One is parallel RC circuits dissipation factor, which is equal to 1 by omega RC. Okay, you got that. Parallel RC circuit Q factor, it is omega RC. So can I conclude for parallel RC circuit or series RC circuit, dissipation factor equal to what, my dear? 1 by Q factor. 1 by Q factor. Can I write like this? Of course I can write, because here Q factor equal to omega CR. Take the reciprocal, it will become 1 by omega CR. That is nothing but the dissipation factor. So dissipation factor is nothing but 1 by Q factor. Correct? So I can write like D is equal to 1 by Q, simple. You can remember like in easy manner, like dq equal to 1. Here one and only one Dulquer Salmaan is there na, in Kerala film industry or South Indian film industry. Only one Dulquer Salmaan is there. So Dulquer Salmaan is short name by what? DQ, DQ. So DQ equal to 1. Only one Dulquer Salmaan, DQ equal to 1. So very easy manner you can remember this. Dissipation factor and Q factor relationship is nothing but DQ equal to 1 or D equal to 1 by Q. Anything you can say. Is it clear, my dears? Is it clear? It's very easy, but some equations you have to play with this equation and do. Okay, these are some factors. See, there is some application of this. It is actually in high voltage, underground cable losses and all now. So there you can apply this concept, loss factor and loss tangent and this dissipation factor, etc. There you can apply. But as far as the examination point of view, it is not that much important. That much, which means that application and all, that is not important, but simply the definition and the relation dq equal to 1. You have to note that all. You have to note that's all. Or tangent angle, loss angle or tangent angle, you can correct. Tangent angle, loss angle or tangent angle. Is it clear, my dears? Can I remove this? Okay, can we do some problems so that it will be the idea should be concreted. Okay, if a 200 volt connected to single phase induction motor carry a full load current of 10 ampere at 0.866 power factor over a time period of 30 minutes. Calculate the energy for the half load half load if the energy meter rotates full stop. Calculate the energy for the half load, full stop. If the energy meter rotates 100 revolution in 30 minutes, find the meter constant. Find the meter constant. How can we write? How can we solve this? This type of problems you may expect in your examination. This type of problem you may expect in your examination, my dears. How can we solve this? Read the question carefully. If a 200 volt is connected, so we can write the given data first. V is equal to 200 volt. Carry a full load current of 10 ampere, so IFL is equal to 10 ampere. At a 0.86 power factor, so power factor is nothing but 0.866, or which is nothing but cos phi, comma, over a time period of 30 minutes, so T is equal to 30/60 hour. Calculate the energy for the half load. First you have to find the energy for the half load. So let it be E1/2. Energy at half load. Okay, it's easy now. So E1/2. What is E1/2? Focus. So what is the equation for energy, my dear? Energy is nothing but the energy is nothing kilowatt hour, right? Kilowatt hour. So kilowatt hour means I can write like VI cos phi divided by 1000 into time in hours. Correct na? This is for kilowatt. This is for kilowatt, my dear. Kilowatt. VI cos phi by 100 is kilowatt. Into time in hour is nothing but the into time in hour is nothing but the total energy. Energy is equal to what? Reason, my dear. Energy is equal to what? or power is equal to what? Power is equal to work done by time na. So work done is nothing but power into time na. Power into time is nothing but work done. Work done is same as energy, that's all. So power into time will give you the work done, I mean energy. Is it clear? So power is nothing but VA cos phi. Active power, correct na? So how can I write like V is there, 200. I at half load, it is na, half load you have to find energy. Calculate the energy for the half load you have to find. Half means what? Full load current is 10 ampere, so for half load is 5 ampere, which you cos phi is given as 0.866. Time is given by 30 minutes, so 30 by 60 hour, so 1000. You can solve this and you will get a value of 0.43 kilowatt hour. So kilowatt hour is the unit of the energy. Kilowatt hour is the unit of energy. Is it clear, my dears? Is it clear? So that is the A part. Then what is the B part? What is the B part? What is the B part? If the energy meter rotates 100 revolution in 30 minutes, find the meter constant. So whenever you ask for the meter constant, yes, definitely you have some equation. The number of rotation n is proportional to, or simply n equal to some constant k into kilowatt hour. You already learned the basic principle of an energy meter na. N, that is the number of rotation, is equal to directly proportional to kilowatt hour. It is actually n proportional to kilowatt hour. So if you remove the proportionality constant, you will take it as another constant. So n is equal to k into kilowatt hour. This basic equation, where k is nothing but the energy meter constant. Energy meter constant. So which is nothing but, my dear, which is nothing but n by kilowatt hour. N by kilowatt hour. Am I correct? So it makes what? 100 revolution in 30 minutes. 100 revolution in 30 minutes. Correct na? 100 revolution in 30 minutes. So 30 minutes is already there na. 30 minutes for the same energy meter, not another energy meter. So what the answer will be? 100 divided by, what is the kilowatt hour? You already got 0.43. 0.43. If the energy meter rotates 100 revolution in 30 minutes, that means for these 30 minutes, my dears, for these 30 minutes, what? The energy, I mean the revolution is 100 revolution. So for this half same load, for the same load you have to find the energy meter constant, not for the other load. It is just a sub question, not another question, right? So you don't confuse it. So it will be 0.43, right? 0.43. So if you solve this, you will get what? 100 by 0.43, you will get 232. Okay, that much revolution per kilowatt hour. So this is the energy meter constant. Revolution per kilowatt hour. So it is very, very important. This term now, this is very, very important. In examination, kilowatt hour is not given. Suppose just B part is asked. Most of the examination, we expect the B part. So for that, n equal to k into kilowatt hour, energy meter, I mean rotation will be given. So kilowatt hour you have to calculate by using this. For full load means it is simply VA cos phi divided by 1000, not half load. It is for full load instead of. If it is not specifically as half load and all, then you can take for full load current, that is equal to 10 ampere you can take and find out. That's all. That's all. Is it clear? Is it clear, my dears? Is it clear, my dears? Okay. So that's all. Okay, write another question. Write another question. The meter constant of the meter constant of a 230 volt 10 ampere watt hour meter is 180 revolution per kilowatt hour. The meter is tested at half load and rated voltage and UPF unity power factor. The meter is found to made the meter is found to made 80 revolution per in 138 seconds. Determine the meter error at half load. Half load. Listen, question. Read the question carefully, my dears. Read the question carefully. Okay, listen. We can write the given data. V is equal to nothing but 230 volt. Watt hour meter or energy meter, no? Same meter, same name. A kilowatt hour meter or energy meter, you can use any name, no issue. Okay. I is nothing but 10 ampere. That is the full load current, right? Full load or I is equal to 10 ampere. And the energy meter constant is given by the K is equal to what, my dears? 1800 revolution kilowatt hour. That's also fine. The meter is tested at half load. The meter is going to test at half load and rated voltage. So 230 volt, no issue. At UPF power factor condition. So cos phi is equal to what? 1. The meter is found to made 80 revolution in 138 second, my dears. Determine, during that testing, the meter is at going to test at half load. So during the test, the meter found to made 80 revolution in 138 second. Determine the meter error at a half load. I will tell you the step by process. Let kWh1, that is the kilowatt hour 1 is calculated like what I see. The total, the energy meter constant is 1800 revolution per kilowatt hour. What is the meaning of that? For 1 kilowatt hour of consumption, or for 1 unit consumption, 1 kilowatt hour of consumption, the energy meter should revolve how many times? 180 revolutions. It should 1800 revolution it should make. Then only there will be 1 unit or 1 kilowatt hour consumption. Then for 80 revolution, what will be the consumption? You can directly say from the rotation itself na. So 80 divided by 180 kilowatt hour na. 80 divided by 1800 kilowatt hour will be the corresponding energy consumption. Directly from the energy meter constant, you can, if you have an energy meter and it have a constant, say 2000 revolution per kilowatt hour. Suppose it makes 20 revolution. How can we calculate? You take a pen and paper and you directly, you read like this, VI cos 5 kilowatt hour by converting it. No need, because energy meter constant meaning is that this much revolution for this much kilowatt. For example, my dears, suppose an energy meter is rated like 2000 revolution per kilowatt hour. per kilowatt hour. Then suppose it make 1000 revolution. What do you infer from this? What do you conclude from that? Okay, it consumed 0.5 kilowatt hour. That's all. That's all. So same way, suppose it made 80 kilowatt hour, my dears. So what will be the energy consumption? What will be the energy consumption? Which is nothing but 8 by 80, which is nothing but, if you do this, you will get like 0.0444. 0.0444 kilowatt hour. 0.0444 kilowatt hour. In examination, this much difficult points will not be there. Simple cut and like that, no? 200, 2000 and 1000 revolution like that you will get, okay. And let the same thing I am going to calculate it in different manner. Let it be kWh2, kilowatt hour 2. It is given that what? Normally, how can we find the kilowatt hour rating? Vi cos phi divided by 1000 into time. T in hour, correct? T in hour. So let's do that. 230 into I. I is nothing but half load it is clearing. So 5 into cos phi it is 1 divided by 1000. Divided by 1000 into time in hour. 138 second, my dear. So it will be 138 divided by 60 minute into 60 hour. Is it clear? So if you solve this 230 into 5 into 130 divided by 3600 into 1000, if you solve it, you will get 0.04408 kilowatt hour. This is, let it be kWh2. kWh2. Okay. Is it clear, my dears? Is it clear? Is it clear? So actually, what is the meaning of error? Error or percentage error will be equal to measured value minus true value divided by true value into 100,000. Clear? What is the measured value here? Measured value is nothing but our first one, kWh1, right now? True value, you found out by the actual happening in the what? Voltage, current, power factor, etc., etc. That will be most true, na? This will be most true or most reliable value, na? But this is nothing but you simply calculate from the energy meter constant itself. It may not be, it never be a true value, because suppose you you calibrated your energy meter 3 years back. At that time it was 1800 revolution per kilowatt hour. Due to friction, due to overcompensation, due to spring delay, due to that train arrangement weakening, it may not be 1800 rpm now after 3 years. So that will be definitely the measured value, not the true value. So it will be kWh1 minus kWh2 divided by kWh2, where kWh2 is nothing but the true value, my dears. So it will become 0.0444 minus 0.0408, 0.0408, 0.04408, okay, 4408, 4408. So it will become, is the answer yes. So nearly you will get 0.9%. Nearly you will get 0.9%. Okay, and if error is positive, energy meter advances. If error is negative, energy meter speed reduced. This thing you have to note. If error is positive means it is the energy meter running fast, or simply the speed is increased over time, or if it is negative means, suppose you got minus 0.9, my dears. So it is an indication that after a period of time, what happened, your energy meter starts slowing, or the speed reduced, okay. The concept is very, very important, my dears. The concept is very, very important. Okay, next question. A 230 volt 5 ampere energy meter is tested at its marked reading resistance of PC is, resistance of PC is 8.8 kilo ohm and the current coil is, and CC is 0.1 ohm. Calculate the power consumed by A, normal loading, and B, phantom loading, bracket, by connecting 6 volt battery to get a full load current, Read the question carefully, my dears. Read the question carefully. So see, I already drew the do the circuit diagram for the, or equivalent circuit diagram, for the energy meter, correct? So this is the energy meter. So this is nothing but, my dear, current coil, and this is pressure coil. So we are giving what? 230 volt, and due to that there is a flow of current of 5 ampere. Okay, that is, this energy meter is testing, my dears. Testing means definitely it have certain load, correct na? Definitely it have certain load. Power consumed by K. What is we have to find? Resistance of the pressure coil is 8.8 K, you know, this one. So I can write it R pressure coil, or RP, simply pressure coil is nothing but 8.8 K, and RC is nothing but resistance of the current coil is nothing but 0.1 ohm. And what is that? Calculate the power consumed by normal loading. Suppose it is normally loaded. This is the normal loading figure. current coil is connected in series with the load, definitely there will be flow of some load current, and pressure coil is connected across the load, so definitely this is the normal loading. So what is the total power consumed? Total power consumed will be, I can write like the my dear, total power consumed here by the energy meter, no, because energy meter is going to test, energy meter is going to test. So the power consumed by, that means suppose it's a load, my dear, it's a load, so definitely this energy meter will show how much energy it consumed, right? How much energy it's consumed. Power into time will give you, definitely into time will give you the energy. Okay, energy meter and the power, I mean watt meter are similar in construction, only that time factor is there. Okay, so and time factor to we are calculating, correct na? We are calculating. So total power consumed, I can write like, suppose this is the pressure coil voltage, so I can write one more thing, my dear. The pressure coil voltage is nothing but, my dear, 230 volt, and the current coil current, let IC is equal to what? 5 ampere. 5 ampere. So the total power consumed will be, I can write like Vp into IC, pressure coil voltage into current coil current, okay, plus Vp square by Rp. Am I correct? Because why I take like this? This the total power consumed by the system will be equal to Vp into Ip, that is 230 into 5. 230 into 5, that is the total power consumption by the system, plus what? The small amount of power consumed by what, my dear? This pressure coil also. The small amount of power consumed by the pressure coil also, that is nothing but Vp square by Rp. Vp square by Rp. So why I didn't take for current coil? Because current coil is very low resistance, its resistance is very negligible, so that it will not consume any power or energy. Is it clear? So it will be Vp into IC is nothing but, my dear, 230 into 5 plus Vp square. Vp is given, right? 230 square divided by Rp. Rp is nothing but 8.8 kilo ohm. So if you solve this, you will get a value of 1156 watt. That is the total power consumed. Okay. Okay. This is the case 1 or A for A question. Next one for B question. Can we do that? Is it clear? And what is for B? And what will be for B? What will be for B? So we are using a phantom loading. So now it will be clear that why the phantom loading is we are using why the phantom loading we are using for the energy meter testing. You will clear now. So phantom loading, my dears, I already told you that suppose this is the current coil and this is the pressure coil. Current coil and this is the pressure coil. So what we are going to do is yes, 230 volt is applied here. A separate power is there for the pressure coil, and that is nothing but, my dear, 6 volt. That is nothing but 6 volt. Okay, so this 6 volt, what is in the question? Yes. So what here, see here my dear, so due to this 230 volt there is a current of 5 ampere, there is no change in that. Okay, there is no change in that. Calculate the power consumed by normal loading and phantom loading by connecting 6 volt battery to get full load current. Full load current is means the normal current is there. Previous it was 5 ampere, so now also it is 5 ampere, there is no change in that. Okay, so now the power will be now the total power will be what, my dears, which is equal to the voltage across the pressure coil into the current through the current coil. Am I right? So the voltage across the pressure coil means what? The voltage across the pressure coil means 6 into 5 plus and 6 square divided by RP. RP is nothing but 8.8 kilo. See the difference? There it was 230 volt instead of these 6s. Now we are providing, yes, please note one thing. Power is nothing but in wattmeter, how that wattmeter is reading power. You should know that first. It simply read what is the voltmeter, what is the potential coil voltage? Okay, 230. What is the current coil current? Okay, 5. 230 into 5. That is the product. You are seeing on the watt scale. So the wattmeter just check what is the pressure coil voltage and what is the current coil current. That's all. Only these two things that will notice. Whatever may be the pressure coil, current coil, this is the current coil across the voltage applied, current coil across which you apply the voltage. It doesn't have any meaning on this wattmeter. Normal condition, normal working condition. It is simply check what is the pressure coil voltage and what is the current coil current. That's all. Now suppose in ordinary condition, this is actually connected across the supply or load. That is why this pressure coil voltage is the rated voltage or the applied voltage. Into the current meter, current coil current is 5 ampere. But now what? The pressure coil voltage is not 230. The pressure coil voltage is not 230, but it is 6 volt. Now it is 6 volt. So pressure coil voltage, what is that? 6 volt. Current coil current, what is that? 5. 6 into 5 plus array for losses part. Okay. Current coil doesn't have any much resistance, so its losses can be neglected. But the pressure coil have very high resistance, so they will contribute some losses. Okay, take it is the pressure coil voltage, again 6 Vp square it, divided by the pressure coil resistance Rp. That's all. So if you do this, you will nearly get an answer of 30 volt. See the difference, my dear. In previous question, that is in A part, it's A part. For normal loading condition, you normally loaded and tested, right? So for 5 ampere loading, you tested in some manner. So at that time, you got 1 by 56 watt. You got 1 by 1156 watt. Suppose by same testing can be done by the phantom loading also. What was the procedure for phantom loading? What was the aim of phantom loading? In order to neglect, or in order to reduce the huge losses while energy meter testing, we are using the phantom loading. Or there is some cases where we can't get the exact load or heavy load for testing some energy meter. There also we are using a phantom loading. So phantom loading means nothing but a low voltage supply is connected to the pressure coil of the wattmeter or energy meter, and that supply voltage is adjusted in such a manner that the rated current will be flowing through the current coil. That's all. So 5 ampere is a current coil current, and the total power will be now nearly 30 watts. This much huge difference is there while doing the what? Sorry, my health is not good. Okay. It has been almost 3 to 4 years suffering from cold, normal cold. Okay, so this is the answer, and this is the difference. So this much difference will be there, my dears, in phantom loading. Okay. So by 36/20/22 assistant electrical examination, assistant electrical inspectorate examination will be there. So definitely within 3 months, now it is almost 3 months is there. Within 3 months I will complete all the syllabus. All the syllabus. I can guarantee that I will complete all the syllabus, but I don't get the time to previous year's question paper analysis. If I get suppose 2-3 months more, that means definitely if you are preparing for sub-engineer or assistant professor exam and all, definitely it will be, we will complete the complete previous year question paper revision. But for electrical inspectorate, I don't think so I get time to revise the previous year question paper because it is hardly 3 months there. So measurement we are going to finish by today, tomorrow or day after tomorrow we will finish measurements. After that again very big subject, right? Power system is there, analog electronics is there, no? Again so many subjects are there, so I will try to complete it by within 3 months. All syllabus I can complete, but I don't think so I get time to solve previous year question paper. So it's your duty to do for now, at least for this electrical inspectorate exam, you have to prepare by your own self previous year question and all. And after that electrical examination, for preparing for sub-engineer and assistant professor exam, definitely we will do the previous year question paper analysis. Okay. And until then, please share my videos to all of your friends so that our family should be bigger and bigger. Our family should be bigger and bigger. A wattmeter connected, write a question. A wattmeter connected in a circuit reads 5 kilowatt. After 5 kilowatt, full stop. After interchanging the terminals so of current coil, terminals of CC, this is current coil, it reads 2 kilowatt. Find the total power consumed by the load. Listen, my dears. In this question, a wattmeter connected in a circuit reads 5 kilowatt. Normally what happened, suppose this is the wattmeter, and it reads 5 kilowatt initially. No problem, it reads 5 kilowatt, okay, fine. After interchanging the terminal of current coil, it reads 2 kilowatt. That means the current coil is nothing but what? This is M, L and this is CV. That is the terminal of the wattmeter. I already told you, this is the terminal of the wattmeter. So this is for load. After interchanging the current coil means what happened, my dear? This L is breaked here and this is breaked here. Like this. So initially the flux here was in this direction, but now the flux here was in this direction. But now also it reads the positive, means actually the negative power is happening there. So in the laboratory you may experience a problem like that. Suppose you connected everything and you started reading, take reading, and suddenly you notice one thing. One meter is positive direction is moving. Okay, fine, that's a good wattmeter. But another wattmeter, you notice one thing, it is moving backward. So definitely the lab assistant will say, "Arey, that wattmeter is wrong. Your connection is wrong. You change any of the terminal, you interchange either pressure coil or current coil, you can interchange." So what now normally we interchange M and C. Or we interchange M and not M and C, we interchange M and L normally. So what happened then? Then it will be positively reading, you can go for that. That means if we perfectly connect one wattmeter and it reads positive reading, at same wattmeter for same connection, if you interchange then also it will read positive reading, means the effective power, you have to note this, my dear, that the effective power consumed by load in this situation will be equal to, or simply W is equal to W1 minus W2. Simply you can write like this, W1 plus minus W2. You have to add two values, my dear. One is 5 and the other one is minus 2. So it will be 3 kilowatt will be the reading. This is the actual power consumed. It's the actual power consumed. Okay. You interchange the terminal means what you did? You make the polarity of the magnetic field in opposite direction. So you have to subtract. Okay. Next, it's actually a small theory. You can check it. How can we a reactive power measurement by a wattmeter on a 3-phase supply. So listen, my dear, it is simple. Suppose you have a wattmeter in your hand. By using that wattmeter, if you want to calculate the reactive power, normally wattmeter is used to find the active power, but if you want to calculate the reactive power using a wattmeter on a 3-phase supply, what we have to do means you have to connect the current coil across any of the line, and the pressure coil nowadays, the pressure coil you have to connect in this manner. The pressure coil you have to connect in this manner. The pressure coil you have to connect in manner. So the wattmeter now read wattmeter will be equal to the voltage between B and Y and the current through this IR into cosine of the angle between VBI and IR. That is the cosine of the angle between voltage and current. If you solve this, if you draw a phasor diagram, if I do this, if I can do that, okay, I will do. This is VR, this is VY, this is VB, this is IR, because it is an inductive load now, so it will be definitely lagging by an angle phi. IB, IY, phi. So VBY we have to find now. We have to find the angle between VBY and IR. So VB is there, Y is there, then what will be VBY? This is minus VY. So the total this angle will be what, my dear? 60. Total this angle will be again 60. So the resultant again, and this angle will be what, my dear? 30, and total this angle will be what? 30. So this is VBY, correct now? So you have to calculate the angle between VBY and IR. So VBY, see, 30 plus 60, 90 plus 5, 90 plus 5. So it is again what, my dear? VBY into IR cos of 90 plus 5. Cos of 90 plus 5. What is cos of 90 plus 5? It is nothing but minus sin phi. So what is the equation for reactive power? VI sin phi. For 3 phase it will be 3 into VI sin phi. So simply multiply. So how can we find the reactive power? You can simply multiply the voltmeter reading by 3. That's all. You will get the total reactive power in the 3-phase system. You can get the total reactive power in the 3-phase system. So multiply the wattmeter reading hence obtained by 3. By 3 you will get total reactive power. That's all simple. That's all simple. Is it clear, my dears? Is it clear? Is it clear? Is it clear? Is there any doubt? There are two types of instrument transformers. One is current transformer and second one is voltage or potential transformer. Potential transformer. Let's learn first current transformer. Please draw the circuit diagram. Listen, my dear. So current transformer is very, very important in measurement purpose. So why the name instrument transformer means, suppose in our transmission line, you have to measure the current. Okay, that is the current. Suppose the current is in the range of, not in the of course you can take in the same transmission line. Suppose your current is 10 ampere, but you have just 1 ampere ammeter in your hand. The current which is flowing in the transmission line is 10 ampere, or load, not transmission line, or even in load side, your current is 10 ampere, but unfortunately you don't have a meter, that is the ammeter, to measure that much current. Only you have 1 ampere current, 1 ampere ammeter in your hand. Is it possible to measure the load current by using that 1 ampere directly? No. The what meter may damage, because it doesn't have the capacity, that much capacity. So at that time, within our meter range, any load current can be calculated by using the current transformer. So current transformer means, ideal current transformer means, my dear, single primary winding and infinite number of secondary winding transformer is termed as the current transformer. Normal work construction and everything is same, but in practical current transformer, only few number of turns windings are there in the primary side. So this is the primary side, and very large number of turns will be there on the secondary side. So how it works? See, this is the big current you want to measure. This big current is moving like this, and it will go to this few turn winding. So definitely some magnetic field will be there. It is some another conductors are there, which is in the same magnetic field. If this is changing, there will be a induced EMF in the secondary by mutual interest, the normal transformer action. There will be some induced EMF. So see, the number of turns here is very high, very high. So we have the basic equation is that I1 by I2 will be equal to N2 by N1, my dears. I1 by I2 is equal to N2 by N1, or I can say that is I2 will be equal to N1 by N2 into what? I2 will be equal to N1 by N2 into I1, or N1 is what? Very few number of turns. N2 has very huge number of turns. So N1 by N2 will be what? Very less, very less. So I2 will be very low current as compared to I1. So by our meter, small meter, you can calculate the current here. Calculate the current here. Suppose here it is 100 ampere flowing. You just have a 10 ampere meter in your hand. Okay. So you measured what? You measured by using the 10 ampere full scale deflection you got. So 10 ampere is the current indicated by your meter. This is the current which is flowing through the line? No. You have to multiply it with the turns ratio, N2 by N1. So N1 by N2. No, N2 by N1 is correct. N2 by N1. So what do you get? 10 into N2 by N1. N2 is huge number of turns, N1 is small number of turns. Correct na? So you will get a huge current. So the current can be measured indirectly. So current transformers are used for just measuring the current, which is very high in magnitude, but in our hand there is not that much high level of meters. So by using our own meter, you can measure the current by connecting it via a current transformer, so that the current transformer reduces the current, and which can be easily detectable by your small meters. That current is not the actual current. If you want to get the actual current, multiply this current with the turns ratio, then you will get the high current. That's all. Is it clear, my dears? Well, clear? That's all. So I2 you measured, this current will be very small. So if you want to find I1, then I1 will be N2 into I2 divided by N1. That's all. N2 by N1 into what? I2. So you will get the big current. You will get the big current. Is it clear, my dears? Is it clear? So that is the simple concept of the what? Current coil. Okay. And see, in current coil there are two types of errors in CT. It is very important. One is ratio error. What is the ratio error, my dears? See, normally in current transformer, N1 by N2 will be equal to I2 by I1. Am I correct? Normally it should be valid, right? N1 by N2 is equal to I2 by I1. But due to some problem, that means due to some reasons, the reason is one thing, very important reason is that the whole of the current now, this 100 ampere current, which cannot be completely transformed to the secondary, which cannot be complete, that means the whole flux due to the 100 ampere current now, which is cannot transferred completely to the secondary, but a smaller portion will be utilized for setting up of flux in the core, setting up of flux in the core. That means it is utilized for the what core loss component. Core component you studied in the what shunt component, shunt branches in transformer equivalent circuit. This is RW and this is XM. You learned, right? So utilized for setting up of this a small current, that is I0. You already learned. So from the applied current I, a small portion is usually here. Only the remaining will be there. I minus I0. So that complete current you applied here is not transformed completely to secondary, but only I minus I0 is transformed secondary. So due to that, even though we make N1 and N2 very perfectly, and we have N1 number of turn, N2 number of turn, ideally our imagination is that, oh, this should be equal to I2 by I1, but never. This equation not satisfy in CT, in practical CT. That means ratio doesn't match. This is due to the fluxic setting. This some current is utilized for the flux setup. So this is called, my dear, nominal ratio. This is called actual ratio. That is the actual ratio you obtained. Nominal means ideal it should be, but actually you obtained this I2 by I1 if you measure some currents and all. Okay, so a ratio error is defined as nominal ratio minus actual ratio divided by actual ratio. So percentage ratio will be equal to into 100. This equation you have to note it, and you have to note one thing, this ratio and phase angle error. There is one more error, phase angle error. The ratio error is due to the magnetizing component. It is due to the magnetizing component of what? The flux setup. Okay, magnetizing component of flux setup. Ratio error. Is it clear, my dears? Next error is called the phase angle error. I will tell you that also. Actually, it is a very big derivation and all is there, but for examination point of view, it's not that needed. Next error is phase angle error. So phase angle error is the concept is that, my dear, normally the angle between primary and secondary currents should be 180. Correct na? Primary current and secondary current should be 180 degree out of phase. You know this, right? The primary current is flowing like this, the secondary current is emerging like this. So the angle between these two will be 180 degree. But in some reason, due to some reason, the primary and secondary currents which is not equal to 180 in practical. Or in other words, my dear, the angle between primary current and secondary reversed should be 0 degree, but practically not equal to 0. The same definition you can use anything, any of the two you can use. What is the meaning of the second one? It is the angle between primary and secondary. Means suppose this is the primary current, my dear, IP, and this is the secondary current, that be IS. So this should be 180 degree in ideal cases now. And in other words, suppose the IS is reversed, means it is again come here. It is reversed here, means for ideal case this IP and IS should be in overlapped position. This should be overlapped here, so that there will not be any angle. Okay, but practically what happened, my dear, if it is reversed, even if it is reversed here, there will be a small angle del. Will be there in between that primary and secondary reversed current. That del will be in the range of 1 degree or 2 degree. That del corresponding to an error which is called the phase angle error. And there is an equation, just you have to remember this equation: 180 by pi into Im cos del minus IE sin del divided by n into Is. Just you have to remember this equation, my dear. This is called the magnetizing component. This is called the working component or energy component. Working or energy component. This much degree in degrees. You just remember this equation, 180 by pi into Im cos del minus IE sin del. So phase angle error is due to both the component of magnetizing as well as the working component. Okay, that's all about the current coil. I mean the current transformer. And my dears, same thing will be there in the potential transformer also. And their ratio error is nothing but error is due to what? I will tell you that their N1 by N2 not equal to V1 by V2. In potential, give importance to voltage. In current, give importance to current. That's all. Due to some reason. This reason is same as that before. The magnetic flux setup will utilize some of the current that we applied, so there will not be disproportionality. This is called the nominal ratio, and this is called the actual ratio. Okay, so there will be percentage ratio error, is equal to nominal ratio minus actual ratio divided by actual ratio. That's all. And potential, there's a phase angle error, very big equation is there. No one will ask you. This is very complicated equation for potential transformer, but definitely it won't ask for your examination. Okay, you can't neglect it. So that you can neglect it. Okay. Is it clear, my dears? Is it clear? And you can substitute, suppose cos del is equal to 1 here, del will be 0, so this component will not be there. So you can directly take a theta equal to 180 by pi into Im by ns. Im by n into ns. This n into is now, which is also the IP. N into is equal to IP, my dear. N is nothing but the turns ratio, right? N is nothing but the turns ratio, where n is the turns ratio. N into is equal to IP, where n is equal to N2 by N1. Okay, N2 by N1. That small n is called N2 by N1. Okay, this much deeper question will not be there. Okay, but anyhow we have to prepare, right? Anyhow we have to prepare for the utmost conditions. Okay, so that's all for today, my dears. Let's meet again tomorrow with a new session. So until then, bye.